All right, so here's part 2 to section 7.2, matrices and linear systems. In the last video, we showed you how these guys were solutions to our differential equation, our system of differential equations, and we just gave them to you. We'll show you how to come up with these guys next time. And if each individual piece is a solution, then any scalar multiple of each piece added together then is an overall or general solution. Okay. Now think back to chapter 5 when we talked about having enough pieces for our solution. And enough was, and our way to check for enough was testing if they were linearly independent or not. Okay, and in chapter 5 we learned about the Wronskian as a test for linear independence. So let's go ahead and find the Wronskian for this problem right here. He is a 2 by 2 matrix, so we could do just the AD minus BC, but we could remember also that we can factor out from rows and columns, and then it makes the matrix a little easier for us. So -1, 3, 1, and 2. And whoops, that should be a 4t. So e to the negative t times e to the 4t would be e to the 3t. And we have -2 minus 3, which would be -5. So we've got -5 e to the 3t, which is never 0. Therefore, our two solutions here, and notice that this was the x1 vector and that this was the x2 vector. Therefore, the x1 vector and the x2 vector are linearly independent. Because they're not identically equal to 0. In fact, they're never 0. Okay, so let's tie into stuff we've done before. Back in chapter 5, we learned how to solve a non-homogeneous system. And the way we do that is to first solve the homogeneous system for the complementary solution, then find a particular solution that picks up the non-homogeneous piece, and then we make the complete general solution by adding the particular solution to the complementary solution. So let's go ahead and do that right now. Let's verify that x sub p vector being 1/8 plus 3/2 t minus 5/4 minus t is the particular solution, or a particular solution, to this differential equation system, where you notice that this is the exact same, but now we've introduced some non-homogeneous parts here. And then once we've got this guy, we'll combine it with our complementary solution, which incidentally we've just been doing. We just found those guys here, and we'll combine them to make the general solution. Okay. So let's move this up here a little bit. And let's do that. So to show that this guy satisfies our differential equation, I need to show that xp vector prime is equal to our matrix times xp vector plus our f vector, the non-homogeneous pieces here. So again, xp vector would be this guy, 1/8 plus 3/2 t, and then in the second component, -5/4 minus t, and f vector is 5 minus 2t. Okay. All right. Well, if this is x sub p vector, then x sub p vector prime is going to be, take the derivative of this with respect to its independent variable t, and we'll get 3/2 and -1. So let's go ahead and take our p matrix. Remembering that our p matrix from last time was 2, 3, 2, 1. And if we multiply that by the x sub p vector, which is 1/8 plus 3/2 t and -5/4 minus t. Okay. Notice that this is a 2 by 2 matrix, and this is a 2 by 1 matrix because of the plus and the minus here. So when we multiply this, we should end up with a 2 by 1 answer. So if I do p times x sub p, we'll get 2 times 1/8, which is 1/4 or 2/8, plus 2 times 3/2 t is 3t. Okay. And then let's do this guy right here. 3 times -5/4 is -15/4. Wait a second, hang on. This times this. Yeah, okay. And then minus 3t. Hang on just one second. Okay, so we have to be a little bit careful because of the plus. So first row times first column. Now let's do first row times first column here. 2 times 1/8 is 1/4 plus 3t, and then minus 5/4 minus t. Okay. Now note what we've just done here. We've done p times the p matrix times the x sub p vector. Okay. But what else do we need to do? We need to do p times the x sub p vector plus f. So now let's take this guy and add the f vector. So if I now add the f vector, p x sub p vector plus the f vector is going to be this guy right here. Let's see, we've got 1/4 minus 15/4 is minus 14/4, or -7/2. And 3t minus 3t is 0. 1/4 minus 5/4 is -1. And 3t minus t is plus 2t. Okay. Now let's add our f vector. And our f vector, you remember, was 5 and -2t. Okay. So when we add those, we've got -7/2 plus 5. 5 is 10/2. -7/2 plus 10/2 is, let me write that down. And lo and behold, that is 3/2. Whew, that's good news. And then -1 plus 2t minus 2t is -1. And so we have now verified that that is a particular solution. Okay. So now what we're going to do is make the general solution. So our overall solution here is c1 times the x1 vector plus c2 times the x2 vector plus x sub p vector, the particular solution part. Or in other words, c1 times negative e to the negative t and e to the negative t plus c2 times 3e to the 4t and 2e to the 4t plus our particular solution, which was 1/8 plus 3/2 t. Make that 3 look a little better. This pen, I need to get a new one. And minus 5/4 minus t. And we could, if we wanted to, put this all together, getting negative c1 e to the negative t plus 3c2 e to the 4t plus 1/8 plus 3/2 t, and c1 e to the negative t plus 2c2 e to the 4t minus 5/4 minus t, and that's equal to the x vector. And notice that the x vector would be the x1 of t and x2 of t functions. So this guy right here would be my x1 of t. Notice I didn't say vector. And this guy right here would be my x2 function of t, not a vector, because he's just a component. Okay. So I know it's a challenge, but try to keep those guys straight. And what I'll do now is let you practice on this guy, solve the initial value problem. So go back in with this guy, and knowing that x1 of 0 is 1 and x2 of 0 is 1, find the C1 and C2 that satisfy this for our initial conditions.